Swayam Prabha. Digital India. Educated India.
Good morning, students. I'm going to talk about the course Engineering Mechanics. I'm going to lecture in the next 38 or 40 lectures regarding this engineering mechanics. I'm a faculty in the Department of Mechanical at IIT Tirupati at this moment. Before joining IIT Tirupati, I was in IIT Kanpur for 31 years. So my areas of specialization are solid mechanics and design, in particular the finite element methods, composite materials, non-destructive testing, and of course the mechanics and fracture mechanics and so on. So mechanics is my very interesting subject, and then I taught this course a number of times. So this engineering mechanics is just looking at that is a very important course for engineering in the departments of civil, mechanical, aero, and chemical and electrical and so on. So as such, engineering mechanics is the application of mechanics, principles of mechanics to solve problems involving common engineering elements. So common engineering elements in the sense that rods, beams, wheels, plates, and so on, because together they make the structure, together they make the machine. And the goal of this course is to solve problems in mechanics as applied to obviously many real world scenarios. So essentially this is the application of principles of mechanics to many of the engineering problems. And this forms a very core course in engineering, and so I just gave the course content here. So course content has many chapters or topics, starting from equilibrium of rigid bodies, so in the static case, and then we also deal with the free body diagrams, and the system of connected bodies is the final goal for us, and of course continuous systems. Then we deal with the energy and in a conservative system for both rigid body and particles, of course. So then there are so many other principles such as virtual work, which is the other side of the mirror of the basic Newtonian mechanics. Then we go on to the various coordinate systems, cylindrical coordinates, spherical coordinates, and moving axis for the application of the motion. Then, of course, from a simple kind of particles, so we move on to the rigid bodies, and rigid bodies have their own extra difficulties and extra aspects in that, and we deal it at the 2D and at the 3D level also. Going from 2D to 3D is a big jump, and there are many aspects that need to be considered. So this is in a nutshell what we are going to deal with. And then I also listed out the textbooks like Mechanics for Engineers, essentially Vectorial Mechanics by Beer and Johnston, and Merriam and Craig and Shames and Hibbeler. All these books are very concise, very nicely written, very popular books, and very comprehensive books as well. Then the last one, Crandall and all is about mechanics of solids, but only the first chapter has been taken just for illustrative purposes. So all these, so most of the material or the flow of the lectures which I take here follow the sequence in which these textbooks are deal with the topics. Coming to this mechanics, so it's a very important course for engineering. So this forms the basis for all your design and analysis of various structures and machines, sometimes small or sometimes even big. So this forms the core knowledge for the further analysis of bodies for the design purpose. In the sense that design purpose, in the sense that we have to make sure that all the bodies put together to form the machine or to form the structures, they perform satisfactorily without failure or without causing any damage to the humans or even to the neighboring properties. So that is our final goal of the engineering. Of course, in that process, there are many other things like what is the cost, how to minimize the cost, and the materials and all that will come into the picture. But in all these approaches, so what we need fundamentally is that what are the forces to which each component is subjected to. So the machine or structures will have many components, but we should be able to understand how the bodies interact and how each body is going to sustain the forces, because the forces have to be transmitted from one body to the other, like in the case of power transmission. So a force in certain form at one point is transmitted to another point in another form associated with some motion. So that means that all these connected bodies, each one of them should be able to sustain the load to which it is subjected to. So that is the whole idea. And since this forms the very basic core of the core engineering in mechanical, civil, and aero. So without this, let me tell you, so when the engineering person cannot be called a fully capable design analyst. So this is a bread and butter of these engineering branches. So I request you that please pay attention to each and every detail, right from the first topic all the way to the last topic, starting from, let us say, the particles all the way to 3D analysis of rigid bodies. So all these things is built from one topic to the other, to the next topic. Unless somebody is very comprehensively fully understand the first topic, you may not be able to follow the second topic, and it becomes more and more difficult if you try to understand higher topics without understanding the initial topics. So that way, that is the most difficult part of this mechanics. So that means that to go to the last chapter, you have to have command on all the topics right from 1. Okay, so this is a very important course. Usually we teach it over 14 weeks in the institutes, and it has 3 lectures followed by 1 tutorial in the week. So that means that it's essentially about 40 lectures followed by 14, in between 14 tutorials. So it's a very rigorous course, and one should pay full attention to this one. So it is called usually it is 3100, three lectures and one tutorial. And of course, there's no lab and all that. And usually it's given a credits of 4. So we'll deal this engineering mechanics for some 39, 40 lectures in the coming weeks. Okay. So this is, let me also tell you, so the contents of this course, which I have shown there, are very general and which are prescribed in various institutes, colleges or the universities. So in general, we can say that this covers more or less some 80 to 90%. Sometimes it's more, sometimes I don't say it's very much less, and it is little more than what is prescribed in many of the universities. So in fact, that is the better part of this one. So if you have the full command of this course as it is given here, so you can say that you have understood the dynamics or engineering mechanics at this level to a very good extent. So in this class, we just have an introduction. For example, we said that it's many of the engineering structures which we deal, like this is a very tall structures, Burj Khalifa, and it's Dubai, it's there. So it is 828 meters tall and more than 160 stories. So this is one of the very tall structures in the world, and there a lot of engineering has gone into building this kind of structures. So it looks like a static structure, doesn't move, but while designing these kind of structures, not only they have to take care of all the loads which are coming on each and every component, but also what are the kinds of loads. So not only its own self-weight and moving people who are transiting through this one, their weights, as well as many equipments, and further all the more is the other kind of loadings like the wind loading, as well as and definitely the seismic loading. So that means that the vibration which comes during the earthquake movements. So okay, so all these things have been taken in constructing or designing the whole structure, because it involves not only the safety of the building itself, but the safety of the so many people who occupy that. So this is one of the structures just to show, and I remind you again, so our engineering mechanics definitely forms the fundamental core of designing these things. Okay. Then we have many other. This is a moving train, a TGV train designed in Europe by France and so on. So it's one of the fastest trains in Europe, and the speed record is 574 kilometers, 357 miles per hour, and it was at 1990. And there are many other things also which have come later, but this is, and still it's one of the fastest trains. So maybe if you can go through that YouTube things, and then you can actually see how accelerating the whole journey would be, even the testing of that. So these are definitely, obviously, something which is moving at a very high speed and high accelerations. So the design here goes into the realm of dynamics, but even the earlier one also has some amount of dynamics, but these are definitely machines which deal with a significant amount of forces from various causes. And then, of course, these are also again very big structures. Just a hanging bridge by two tall pylons at the two ends, and this is Rusky Bridge, and it's in Russia. There are so many of these bridges, just to show that typical these kind of bridges is this is a 320 meters height and so much long, 1.1 kilometers long. So it's a cable side. Okay, so all these things again look like statics, but then there's so much of dynamics as well involved. So all these things require very strong knowledge of the basic engineering mechanics. And of course, then there are, on the other hand, we also have many motorcycle special Tomahawk high-speed motors with 10 cylinders, and it can reach a speed of 560 kilometers. So you can imagine that how much design analysis would have gone into this one to make each and every component work to the satisfaction. Yeah, just to show that this is about just a car, an automobile car, which has 30,000 parts which are interconnected, and some parts are very vital and some parts may not be that vital, but we should make sure that the forces that are coming on each and every component is borne by the body satisfactorily. And of course, these are some of the simple examples which we have here, is some simple trolleys. So all these things require a lot of, a good design really require a lot of study. Okay, you should be able to study how various parts interact with each other and how the forces are borne by each component satisfactorily. And some of them are just the mechanisms. Of course, it comes more in mechanical as a mechanism. Even that ratchet mechanism may not carry a lot of load, but then it has a lot of motion analysis. And of course, there are very delicate objects which are handled by the robot. For example, here, this is a lot of sensors are there in this kind of mechanical arm, and how they handle the bulb without actually breaking it. So like this, so one of the things that's important here is about the acceleration. So mechanics obviously has two parts. One is the statics, another is the dynamics. And statics is the situation where the motion is not very much involved and it's not significant, okay, like a state of rest, or maybe the motion is of very low velocities or low accelerations. But then there are machines or there are bodies which are subjected to high accelerations also during their course. In fact, they're meant to go through a lot of acceleration. So just to have some idea about the magnitude of acceleration at various situations. For example, people, if it is people, then 001 g is acceleration due to gravity. That is the standard, okay, standard measurement number g, and 001 g, so that means that 0.1% of g that is perceptible by people. And at 0.02 g, if a person is subjected to this kind of acceleration, so the people may fall. For example, if somebody is like that and then suddenly a gust of wind comes, and if he suddenly an acceleration of 0.2 g is impinged on his human body, then he will lose the balance. So this is the third one is 0.5 g, is about the accelerations to which buildings may be subjected to, the maximum acceleration a building can be subjected to during earthquake. So while the base is moving horizontally back and forth, so the acceleration, the maximum acceleration the building can sustain is about 0.5 g. Anything more than that, the building will collapse, because buildings have a lot of these bricks and mortar and all that. So those joints cannot take more than this 0.5 g. And the car acceleration is about 0.44. And you would have seen this fighter aircrafts and so on, which undergo a high g during either acceleration, deceleration, as well as taking curved path. So the maximum a person can sustain is about 8 g. Anything more than that, maybe he may lose consciousness, which they call it as blackout, and he will lose control. So that is the maximum acceleration a person usually can sustain, okay, without losing consciousness. And then of course, there are of course the safety seats in the fighter plane and so on, by which they want to evacuate the plane in case of emergency. So that is of course, it's a 15 g. He has to come out of that plane for the safety reasons, and just for a short time he can sustain. He may lose consciousness, but may not be for long. And then anyway, he'll come out and land using parachutes. And of course, again, this 21.3 is the cosmonauts experienced during aborting. So again, in the space vehicles and all that, again, they are subjected to a very high accelerations during aborting. And then finally, it looks like these seems to be very big, but then if you come to the machines, they're reciprocating engines. So there are high-speed reciprocating engines which run at 5,000 rpm or 7,000 rpm. So there, the piston, which is having a reciprocating motion, so is subjected to a acceleration of 5,000 g. So this is a very high thing. So that means that that acceleration obviously is obtained by the application of the force. So the pistons and all that, you can imagine to what kind of forces they are subjected to. So that means that when you design some of these things, so you should definitely make sure that the bodies can sustain that kind of loading, okay, forces. So this is how we can, the importance of mechanics, either from the statics point of view or from the dynamics point of view. So what kind of forces they are subjected to. So we can have some idea of this one. Okay, so the mechanics which we are going to deal with as different classifications. So of course, I already mentioned that there is a statics and dynamics, which I did not mention here. So statics and dynamics is where you have statics is when the motion or the accelerations which are involved are not there, or even if they're there, they're negligible. So there's static structures are static. There's so many static mechanisms which are there. For example, a cutting plier and so on, which we are going to deal with. And many of these things, for example, this table itself is a static structure. And so the analysis of the forces on the body without referring to any of its motion, when there is no significant motion, so then that comes under statics. And obviously the dynamics is the one where the body is under motion and with unbalanced forces leading to certain motion, say accelerations and so on. So that study is dynamics. So obviously the dynamics is much more involved than the statics. So this also reminds me that the mechanics content is slightly less statics to start with, and we quickly move to the dynamics, in the sense that anybody who can do the dynamic problems can definitely do the static problems, because dynamics has many other more parameters to deal with. Okay, so then we have the classifications or kinematics and kinetics to start with. So kinematics is the one where you deal with the motion as such without the consideration of the forces acting on that. So it is only the relationship between various parameters, how to describe the motion in the sense that displacements and how it is related to the velocities, how accelerations are related to all these things, and how we can measure these things. Okay, so that which will be used later and in various coordinate systems. Okay, and how they move with respect to each other and by themselves. So that is the study of the motion without recourse to the cause of the motion, that is the forces, is the kinematics. So kinetics is the motion of the body under the action of the forces. So that means that forces together with the motion is considered in the kinetics. So this is the next step of kinematics. So this is one classification, that is the motion analysis, as well as the second one is the motion under the action of the forces, that's the kinetics. And then we have another kind of classification which is known as particle dynamics, and then rigid body dynamics. So particle dynamics is the fundamental of the mechanics. Particle dynamics or particle mechanics is fundamental to the mechanics. I'll just tell you why it is. And particle is, you say that it's minute in size, and so how the motion takes place, or how the forces act on that one. So if you study the equilibrium of the particle or its motion, so then it is called the particle dynamics. So that means that the thing, the body under consideration is of a very, very small size. Whereas coming to the rigid body dynamics, where we have a size and shape for the body, and we are going to consider the body as such with having a size and shape. Whereas in the particle, so we don't consider the body as a shape. So in fact, the particle and rigid body dynamics doesn't mean that in the particles we only consider the particles like air particles or molecules. No, it's not like that. So particles, if you take a particle in the space, in the three-dimensional space, it requires only three quantities. So we call it as 3 degrees of freedom. It's x, y, and z, say for example in Cartesian coordinates. So the three quantities are required, x, y, z. Okay, and so that means that completely describes its motion, and of course you can get velocity and acceleration. Whereas when you come to the consideration of the rigid body, so where we have the size and shape of the body, so which means that we require the position of some reference point, say three quantities, and together with that we also need the angular position, the rotational position of the body with respect to the reference axis. So if you have an x-axis, the body is like this. So if it is rotating, obviously some theta has to be prescribed with respect to the x-axis. So a rigid body has, if it has a size and shape, so it requires three angular specifications to describe its rotational position with respect to x-axis, y-axis, and z-axis. So that way a rigid body has 6 degrees of freedom and particle has 3 degrees of freedom in space. Okay, so can we consider rigid body as a particle in some situation? So when do we consider rigid body as a particle in situation? There are two important aspects for this one. I'll tell you. The first one is that if the rigid body is not having any rotation, so that means that it's moving parallel to itself like this one, then we can consider it to be a particle because there is no rotation is coming into the picture. You can treat it as a particle. So that means when rotations are not important or they do not enter the analysis, so then you can consider it to be a particle. But on the other hand, if you consider it to be also having a rotational thing, then it should be considered as a rigid body. So interestingly, there are cases where a body can be considered as a particle or body should be considered as a rigid body. For example, if you take an aeroplane which is going over long distances smoothly, say from or distances Delhi to London or so in which case more or less its orientation doesn't change, and more or less, or even if it changes slowly, so it goes over long distances of thousands of kilometers without too much of rotational motion. So then in an overall sense, considering the overall drag, and if you want to find out how much fuel is consumed and so on, so in that context it can be considered as a particle. But on the other hand, if you take the wing and the tip of the wing, which can have the displacement or deflections for half a meter or so that motion, if you want to consider, so with respect to the size of the wing, the motion of the tip is considerable, and then you have to consider that as, because it also has kind of up and down rotational motion and so on. So their vibrations, for example, so it should be considered as a rigid body, not necessarily rigid. Okay, so like this, so a thing which you consider as a particle or a rigid body. So for example, in the example which is shown on the bottom of the slide is that there's a car. So if you are considering the automobile in an overall sense, so if you want to find out what is the drag and how much friction is there, what is the overall petrol consumption and all that, so you just have to consider it as a simple particle. Okay, now it's not a particle because you just have to find out its motion. But on the other hand, if you want to consider what is happening to the wheels, for example, so wheels are rotating with certain friction on the road, and then if you want to analyze the wheel as such, how much force is there, say centrifugal force and so on, so then it should be considered as a rigid body of a certain size and shape. So like this, so whether you consider a particular body as a particle or a rigid body, so it's up to the circumstances of consideration. Okay, so rigid body, again, though we are saying all the time rigid body, so in fact rigid body, and then there's another factor which is known as flexible body. So that means that rigid body in the sense that the particles in the body will not move relative to each other. The distance between the particles remain constant. So that's how we define the rigid body. Whereas in flexible bodies, then the distances between the particles will change depending upon the deformability of the body, elasticity and so on. So then we have to consider it as a flexible body. But in this course, we just deal with only the rigid bodies, and flexibility or the deformability of the body is not considered. We take that the size and shape of the body remains constant. Okay, so flexibility, how the internal forces interact between the particles at each and every level, so that will constitute the next level of our analysis, so where we talk about the stresses and so on, so where we see how the rupture or how the failure takes place at the minutest level. So that is another strength of materials and so on. So that's the next course of this engineering. And then importantly, there's another classification here, single body and multiply connected bodies. So usually all the machines which you have seen, for example, reciprocating engine has a piston, cylinder, connecting rod, and so many general bearings, and then there's a cylinder head and so on. So if you want to analyze that, so then you have to, it's a multiply connected body, you have to understand each and every one. But then if you want to design a particular component, then we have to know what are the forces that are coming on that, okay, so that you can do the design. So that's why a single body and multiply connected bodies, which are the realistic situations, so we should know how to analyze at both stages. So it's very interesting that if you look at, I'll come back to this one, just I want to show you that if you look at the Newton's laws of motion, the basic laws, so the basic laws, if you know all these principles, so the basic laws is that the first law talks about when it continues to be in a state of rest and uniform motion unless it is acted upon by forces. So essentially there are many slight differences in the definitions are there. The velocity of a particle can only be changed by the application of a force. So if a force acts on a particle, and then obviously its velocity changes. The second law talks about the relationship between the force and change in velocity, which is given by acceleration. So it is F is equal to ma. And the third one talks about the interaction between bodies. Actually, any force here in the world is because of the contact nature. So if the two bodies are there, so if they're pressing each other, there's a contact force, or even the weight which is acting on the body is nothing but it's an interaction between the body and the earth. So everything is the contact forces, and then so this talks about the forces. One is called the action, the other one is called the reaction. So this action reaction work appear as pairs, and then they're equivalent opposites. So you know these three laws. So what I want to point out here is that the first law or even the second law, if you look at that definition, so they talk about on a particle, right? The velocity of a particle can only be changed by the application of force. Even the second one, the resultant force acting on a particle. So the thing here is that the Newton's laws are defined with respect to a particle, right? The definition. So that's why if you go back to this one, so it's very important. We can develop all these laws of motion and static equilibrium, dynamic equilibrium, and all that for a particle based on Newton's laws. But on the other hand, our realistic situations are multiply connected bodies. So that means that we should be able to extend this Newton's laws for a particle to a rigid body, and then we have to understand the interactions, and then we have to move on to the multiply connected bodies. So this is the various stages. In this process, we also look at just the force equilibrium, and also we'll bring the motion into the picture. So we always start from particles, and we apply the Newton's laws for a particle, try to understand that, and then we extend that to rigid body, which will have size and shape and rotation, and then we go to the multiply connected bodies. So it is back and forth, we keep going. So we develop it from particle to multiply connected bodies, and then since we know the forces at multiply connected bodies, so we'll try to go back to single body and probably to internal forces, which we don't do at this stage. So this is how the various stages of the understanding of the behavior of the bodies, and the how this is whole thing is classified. So just to put it in a nutshell again, so what we do here in this course is that first of all we talk about the static equilibrium. So that means without consideration of the motion, without any motion. So we consider the static equilibrium of the bodies or multiply connected bodies, okay, a system of bodies, and try to understand what are various forces coming on this one. After that, so we move on to the kinematics of the particle, okay. So that means that how the motion can be described in various reference coordinate systems. So we'll try to find out Cartesian, cylindrical, spherical, moving coordinates sometimes, and then we try to understand how the motion can be described. Then we move on to the rigid body, so where the bodies have size and shape, and we deal with kinematics and kinetics of the two-dimensional bodies, and we deal with kinematics and kinetics of the three-dimensional bodies. So going from 1D to 2D, 1D you have analyzed to a large extent in your school days, and now here we do it more systematically in a vectorial sense. So that's also which I have to emphasize. Here we deal all the quantities as vectors, forces, and then all our equations are in terms of vectorial form. So it's very important. Okay, so like this, so we go from statics, particles, to bodies, to dynamics, particles and bodies. So this way, nowadays the bodies are subjected to a huge significant amount of forces, and they also undergo a lot of motion, particularly for all these machines. So finally the optimization of all these things, bodies, is very much dependent upon what are the forces acting and how much accelerations that are subjected to, and how the forces, internal forces, are distributed. So that's what we want to finally, well, not here, maybe in the next course. So as far as this course is concerned, we deal with particles, bodies, rigid bodies, and multiply connected bodies in 2 dimensions and 3 dimensions. So I think I'll stop it here, and we will continue in our lecture 2 on static equilibrium. So we'll start with the static conditions, and then we analyze the equilibrium. Okay, so bye bye.